Good morning. Now we're to the most important part of your visit here, of course, because without the data center, they're just photons in the wind, man. So I'm going to talk a little bit about the data center. The data center for DKIST is completely different from any other data center that exists in solar physics. For one, it's actually done properly. If you have to work with SDO data, you will know what I mean by this is actually done properly and SDO isn't. And I can promise, hand on heart, that Valentin, Gianna, none of the scientists have had any role in writing code for a bloody data center. This is good. We have professionals. Shock, horror. Okay, so the data center's role is more than just providing storage for your bits. We do data curation, okay? We're not just gonna, am I too loud? Okay. We do data curation. So we're not just storing the bits on some disks, okay? We're actually gonna look after the data. We're gonna actually provide full data curation through the entire life cycle of the data. So that's from when it arrives here, having been taken off the mountain, all the way through to 20 years from now when you want to go back and look at some paper you wrote and thought, what the hell? We're going to be able to provide you with exactly the same data you used back then, although hopefully maybe the calibration will be a little better in 20 years than it will be when we first get the data, okay? We have to ingest the data, we have to take care of all the metadata storage, the data itself, and we have to try and we have to provide this storage management through a life cycle of approximately 44 years. That's kind of long, 2 solar cycles. Hopefully, in 2 solar cycles' time, you'll have all the infrastructure you need to actually use as much data, you know, as we're going to be getting in those 2 cycles. So the main point of doing this data curation is to reliably ensure that you can get back the data that we took in about 18 months in any number of years in the future, okay? For whatever research purposes you want, or for us to be able to recalibrate it. Yeah, recalibration. Yeah, that scares us. There is going to be so much data that the prospect of doing recalibration keeps us awake at night. Just imagine, you know, we're 1 petabyte in and somebody finds out that we screwed up some of the calibration. And they say, we want you to do it again. And we're like, oh, good. Fraser will give you some numbers about how much data we actually have to process per second to keep up. And it's scary. So we have to calibrate the data to level 1. And Christian yesterday, I think, gave you a really good primer on what we're going to do and what we're not going to do. So we're going to leave something for you to do, okay? And then we have to enable you to be able to search the data and find what you're looking for. Question? Or was it? Sorry, I thought you were just stroking your head or something. Yeah. If I had that much hair, I'd be stroking it too.
I do it a lot, so yeah, it confuses people. What kind of infrastructure is going to do all this processing?
A lot.
A lot?
Yes, I'll get a little bit to that, okay. About the kind of infrastructure that we're actually putting in place.
It's a question I've had for a long time, and I wanted to know, like, what is the dedicated NSO infrastructure to handle that? You'll
actually get to see some of it, or at least where it's going to be, I think, during the coffee break.
So it's going to be a dedicated server?
We have servers, lots of servers. We have a dedicated infrastructure, and it's going to be over in, literally on the ground floor over here, in one of CU's data centers. They very kindly provide us with free power, cooling, electricity. It's really nice of them. But yeah, we will have a full dedicated infrastructure that will ramp up over the years to deal with the data volumes we have for the processing requirements and other things. And I'll come to some of the sort of technical points about that in a little bit. So it's no good just having the data. We need to enable you to be able to query the data, to get it, which when we're dealing with these data volumes is actually an issue, a big issue too. And so we have to sort of be able to do this distribution in a sane and sensible manner. And as part of the data center's remit, we're also going to be providing user tools to make it easier for you to be able to actually use the data. Fraser is going to talk about the data calibration side of things a bit more, and then Stuart's going to talk more about the user tools. So I think Christian yesterday did a really good job about managing expectations for you about exactly what the data center is going to be able to do, especially when we first start operations. The kind of calibrations that we're going to do are going to be based on what the instrument providers will give us to begin with. That's not going to be the last point. This is going to be something that will continually develop over the years as we get more experience with the instrument, understand it better. So it's not a static target, this calibration. And that's what makes the recalibration side of things even more scary, okay? This is, if you come from dealing with space-based data, this one's for you, because you probably run some form of underscore prep, like AIA prep routine in SolarSoft or something like that. So I originally just had this one, but then I realized that, you know, there were some people who've done it with lots of ground-based solar data. So then I came up with this one. Emmy, if you don't know, is Milne Eddington. Okay. Yeah, even as Han will explain, we're not going to be inverting all the lines, right, Han? So we'll do a lot. We'll try desperately to remove those instrumentation and telescope and maybe atmosphere effects for you, but we won't be able to do everything, I think, as Christian very adequately explained yesterday. So in terms of thinking about how we put together a data center, there are a number of challenges which that give us cause for thought and a great deal of thought. DKIST has really broad and deep science goals. It's a complex facility. There's multiple instruments. There is tens of thousands combinations of lines that you could possibly observe with. Multiple instruments, multiple modes. It's petabytes of data a year. And oh, by the way, this isn't a one-time shot. The instruments can be upgraded as we go forward. With VTF, that's actually likely when it goes from 1 echelon to 2. And you know, in the future, people will be able to swap these instruments out for new ones. The data, the veracity, the volume, the type of data, different kinds rather, make it so that we really have to do some form of automated processing with this. Otherwise, the data is just going to sit on disk somewhere and just stay there if we don't provide good basic calibration for the scientists to be able to use. So we have to provide an automated pipeline to do this. If you go back in time, most ground-based calibration appears, at least to me, who came mostly from a space-based background, to be some form of artisanal baking. And by the way, for the Brits in the audience, my scones will beat yours anytime. Artisanal baking and black magic. I mean, I think you saw when Christian was talking that there's a lot of he was talking about looking at data to see where things have gone wrong and how you can try and recognize those patterns for yourself. And to me, that's kind of black magic. So I'm sorry, but the data center wants to take more magic out of the world. Quality control. We actually want to be able to do real quality control to make sure that what you're getting is scientifically valid. And that when we go back and run the codes again, we can get the same thing that we did the first time. Probably we won't do that, we'll try and improve upon it. But we want to be able to guarantee the quality of the data that we're providing. And if you remember Kevin's talk from yesterday, he was pointing to the board at some of the frames as they went by and he was going, meh, maybe, meh. How do you quantify Kevin's meh? We're going to attempt to quantify Kevin's meh, okay? I mean, it was obvious, I think, from most people sitting here when they were looking at the frames where he was going meh, yeah, I know what he means. But how do you actually put that into a form of reproducible quality control? Okay? Long-term data curation, especially for ground-based solar physics, is something which is new. There are synoptic data sets that have been going on for a long time. But the kind of stuff that we're trying to do with data has not been done before. And as I said, we want to build a system in a way that we can upgrade over 2 solar cycles. We can't just go back and reinvent the data center every 3 or 5 years or something like that. Okay? So, I realize, Phil, this actually looks a bit like you. He certainly is. This is a done solar telescope in the background, and the way that a lot of data distribution has been done in the past is you went to the telescope and you walked away with a briefcase full of disks. For that data, in a lot of cases, never ever to be seen again, okay? That's not going to work with DKIST. For one, you'd need a hell of a large briefcase, okay? And when we're trying to provide this data to people, if you're dealing with small data sets, yeah, you can go to an FTP archive. You know, if we could do this kind of thing with DKIST data, the data center would have been built a long time ago. You can't. I mean, how do you search through 300,000 files trying to find the ones that you want? You can't. Not in this kind of layout. So we need something that's a lot more advanced than this. To quote Douglas Adams, it's big, really big, okay? We expect to get about, roughly about 8 terabytes of data a day. But on days of really good seeing, especially when VTF, as you saw from Serena's talk yesterday, is cranking, we could get up to about 66 terabytes of data a day. We only have a 10 gig pipe off from the telescope down to the University of Hawaii. It's kind of hard to actually get 66 terabytes of data off the mountain a day. In fact, we can't. And the mountain only has about 3 full days worth of storage. So it's a bad thing to say, but if there were too many days of good saying in a row, data center would be like, oh God. Anyway, I know that some of you are more visual learners than necessarily just with the numbers, so thanks, Kevin. I have reused this slide so often. This one is kind of where, this is a log scale, by the way. This is where DKIST kind of fits into there. It's slightly wrong now for SDO because they've reprocessed a lot of stuff for, so that they're actually a little bit bigger than that now. But, however, for the truly visual people out there, I present you this one. If you've ever seen me give a talk, you will have seen this little chap before. This is my 800-pound SDO gorilla in the room, because I did a lot of talks on dealing with the data from SDO. And a lot of the challenges are in some ways similar, just scaled up massively for DKIST. So he's no longer the 800-pound gorilla in the room. This is the rest of solar physics, by the way, all the data in solar physics from all the missions ever. It's roughly to scale. I wouldn't argue it's completely to scale, but it's roughly to scale. This is DKIST. It's big, really big. So what are the challenges of dealing with really large-scale data? On the technical side, your standard kind of file systems, things which are in your laptop, or even on servers, or even on those RAID arrays, you know, where you have a bunch of disks and they have a couple of backup disks or parity disks, etc., does not scale well to these really large data volumes. So we need to do things in different ways, certainly in different ways than they've been done in solar physics. Okay? How do you summarize 300,000 results or more? Go back to Serena's talk yesterday in her 2.2 terabytes and how many frames that was. How do you summarize those results for somebody who's searching in a sensible fashion? How do you then enable them to drill down and pull out just the 100,000 they're actually interested in, which was every third frame or something like that? Okay, how do you get that much data to somebody? You know, most laptops have at least 1 terabyte now in, but you know, with Serena's example yesterday, it was over 2 terabytes. You've got space to download that. Okay, that's good. Anybody got 60 terabytes on their desktop to download it to? Oh, come on, I expect at least one person to raise a hand. These are all things that people have to think about. By the way, your 60 terabytes is probably going to take days, if not longer, to download. Okay? In that case, you can't just try and start a download and then, oh, you know, the network drops or your machine rebooted or something and I got, you know, 1.75 terabytes into my 2, I have to restart it again. That is incredibly wasteful on resources, both and on your time and on the data center resources. So you need a system of downloading which is going to be stateful. If interruptions happen, then you can restart the download. You don't have to start it all over again. And also, if you're downloading 2 terabytes and you've waited all that time, we better be damn sure that what you're getting is exactly the same data that's on the data center. And we actually use something, we use a grid FTP solution, Globus FTP, which pretty much handles things like authentication, download. It guarantees the veracity of the data transfer for us. It can continue if interrupted, okay? FITS is the go-to astronomical standard. Certainly in solar physics, that's true. But FITS is actually, even with the more modern implementations, version 4, it's still a very limited file format. Has keywords restrictions. You know, we're still on 8 characters? 8 characters. And it really lacks extensibility. So some of you are probably sitting there thinking, those that have had their coffee, well, why don't you just send it to the cloud, man? We could. We actually could send the data to the cloud. The only problem being is, well, we could just about afford to pay for it to stay in the cloud too. You'd have to pay to take it out. Because the problem with the current cloud infrastructure is that you pay to get data out, okay? And we're hoping that you're going to want to use lots and lots of this data. And so, unfortunately, it would be an unconstrained cost. Even if we say, okay, you need to do most of your processing in the cloud, you know, with compute next to the data. Again, it's an unconstrained cost because we know that some of you are going to go, ha, I've got, you know, 200 terabytes worth of data here that I want to crunch and do something really cool with. Okay? It's only going to take me a week or so of computing time. And suddenly we get a bill for $30,000, $40,000 and we're like, yeah, Valentine, can we have some more money? And he's going to go, no. So we can't put it in the cloud. As I mentioned though, thanks to CU, we have free electricity. Well, free to us anyway, you know, I won't go into the global cost of what we're doing, but in terms of the environment and the rest of it, but we have free electricity, we have free cooling, we have free storage space, and we have a high-speed network that currently is about 40 gig per second, I think, and it's probably going to be 100 gig per second out of this building by the time that DKIST comes online. Those are expensive things to pay for. So as a kind of summary, when we're building this data center for DKIST, we have to be cognizant both of the fact there are scientific requirements for us and also these technical requirements. And then the fact that DKIST is going to be operating for, you know, approximately 2 solar cycles. When we're putting together something now, we have to be cognizant of the fact that this data center is going to last for a long time. So how do we put it together so that, you know, hardware is going to change, technologies are going to change? Well, we build the infrastructure in a way that we can replace components, we can add in new, and we can upgrade as time goes. That's why you need professionals, not scientists designing data centers. So this is the data center science requirements. I don't think when people think of data centers, they tend to think of science, but we actually have a bunch of science requirements, okay, in various areas to do with the data stores, the search and discovery, the distribution, and the data processing that we're going to do. And so this was our top level driver, these kind of science requirements on how we need to satisfy these when we build the data center. This is the simplest overview of the data center there is. You'll notice that some of the colors here will actually correspond with things that were in these boxes here. So we've kind of broken it down a little bit. You know, we have the basic infrastructure of the data center represented right here. And we can devolve that basically into a bunch of what we call these microservices. We tend to break the problem up into small chunks that we can easily define, that we can easily test, because that's important too. We want to make sure that what we're putting together is testable throughout the entire design cycle, okay? So we break all of these tasks up into small chunks, small areas. We create what's called a microservices kind of architecture, okay? This is what enables us to do things whereby we can, on the fly, add more resources in particular areas, throw more computing power, through more storage, etc., particular problems. We can do this on the fly. And we go all the way down to the hardware. This isn't just, we basically have physical infrastructure, compute servers, or storage, whatever we need. We have those as physical systems, and then we put layers on top of those, which virtualizes that environment. And then we create our services within that virtualized environment. This allows us to be really flexible in what we're building and how we're building it, and as I said, in how we can throw more resources at different problems when they come. If we have the mother of all data sets that everybody wants, we can dedicate more resources to processing that to enable people to search and download it, for example. We use a whole different bunch of programs. Most of these are open source, not all. Things like Black Pearl or even, my brain's gone, I need more coffee. Even the Globus stuff, for example, is not actually free for us to use. We pay money for it, but we're paying money in the places where we really need to pay money to make use of the best tools that are available. But we make use of a lot of open source software, which makes us incredibly cost effective for what we're trying to do and what we're trying to build. Open source, it's the way of the future. So Fraser's going to talk more about the calibration of the data, and this is one of our really big tasks. Try and automate that calibration process to get to the data towards a product that people can actually start to do science with, even if, as Christian said yesterday, you're going to have to massage the little data. Oh, sorry, Phil, I didn't mean massage. You're going to have to do extra things to the data in order to get to the point at which you want to do science, okay? I'm going to skip over most of this. I just want to talk a little bit about what we call the ASDIF file. As I mentioned, the FITS file format is incredibly restrictive in what it does. So we're actually along with the data which will be supplied in FITS files, we will be creating what's called an advanced scientific data format file, an ASDIF file. For us, this will contain all of the metadata associated with one data set. One data set is approximately going to be one instrument, one wavelength, one observing campaign. And we can create this ASDIF file which will contain all the metadata for that. And we're going to integrate that with the user tools, thanks to Stuart. And that will enable people to do a lot of things without ever having to download the data. You'll have all the metadata, all the data about the data. You'll be able to download that one file. You'll be able to do searches, which we may not support all of the keywords that you might want to search for in the search interface. But you will have all the metadata available to you. So you can do those searches. You can slice and dice any way you want. And then you can download only the data that you're interested in. So in this way, we're trying to, help you do your science in the most effective way possible, and also help ourselves so that you're not just having to download every data set that you actually are only interested in a part of. So calibration. Here's the very simplified version of the VISP instrument calibration pipeline. I love this diagram, and the reason why I love it is because it looks so deceptively simple. Until you start digging into all of these bits and pieces and yeah, okay. And as Christian was talking about yesterday, even things like geometric correction, overlaying stuff. There's a whole lot of complexity which is going to be hopefully hidden from you. We don't want it to be a black box. You'll have access to the codes, all the documentation about everything that we're doing with the data. It'll all be made available to you. So when it comes to search and discovery, there can be only one API, and there is only one API for the data center. And this is the way in which the web...
Could you define what an API is?
Programming interface. Advanced.
Meaning is some sort of code that is an interface between data and a distribution system? It can be anything, right? An API.
An API is basically a defined way in which you can query something. Okay?
Good.
Is that clear to everybody? Okay, good. So it's the way in which various components of the data center can actually query the data center to find out what holdings the data center has, for example. So the web interface to the data center will use this API. Any command line tools, like the user tools, will use this API. The Virtual Solar Observatory will use this API. And so pretty much everything that wants to query it, including any code that you may want to write to do your particular thing, will be able to use this API. Okay? Rather than writing our own movie browser, we're actually going to use YouTube to provide the movies for you. They'll be referenced from within the interfaces. Unfortunately, we do have to support embargoes as well. So we're going to support a whole bunch of different ways in which you can search for the data. But as I said, I suspect, especially if your name is Kevin, your favorite way of searching for data is probably not going to be one that we support. But through the use of the ASDIF file, everything that describes the data will be available to you to be able to search and do whatever you want with. So, just a little bit more about the ASDIF file. I think I covered most of it, but the important thing to remember is that within the ASDIF file, as I said, all the metadata headers will be there, okay? And you will be able to use this to do a lot more searching and discovery than is possible for us to put into the interface. So, I want to put just one quick slide about the user tools, because they're going to be talked about in a little bit as well. But the user tools are going to be in Python. Just from listening, to people talk or doing the exercises, for example, I think there are a lot of people here who are actually already familiar and using Python for a lot of things. There are many reasons why we actually chose Python. One of them is, we want to be kind of compatible with the NSF open source and open data policy. We don't want to lock people into what is a proprietary system like IDL for analyzing software. We're going to be doing, within the user tools, you'll be able to also, as well, having selected your data, download the data without ever having to get out of the user tools, which for the IDL people or people who use the VSO IDL client, it's your basically search and retrieve is within your analysis environment. Within the user tools, you'll be able to make use of the visualization and exploration stuff that's actually already there within the Python. And you'll be able to integrate, all of this stuff within the wider Python ecosystem. You'll have access to all of the metadata, as I said, and of course all of the FITS files. They'll be there as well. With having all the FITS files, all of the tools which are currently in SolarSoft, they will be able to read all of the DKIST FITS files as well. So if you are still wedded to IDL, there's nothing to stop you from actually using IDL to do your data analysis. And in fact, you could probably use the IDL Python bridge if you want to use some of the Python tools within IDL if you're that masochistic. Hey, some of us are. And the rest is up to you. Subject to Christian's talk yesterday, of course, as he pointed out, when we do these calibrations, there's still going to be a little bit left over for you to do. We don't want to think you can just go and do data analysis or science straight away. All right, that's it from me. Questions?
Was that picture you showed a few slides back like a screenshot of what the ASDF files will look like?
So will you repeat the question?
Oh, so was that screenshot of that I showed of what the ASDF files will look like? Stuart? Okay. Cool. Stuart will show exactly what they look like, but not quite, no.
Fair enough.
Yeah, I have a question about metadata. Like, for example, what will be the responsibilities of the observers? So, for example, if I'm having a proposal to observe quiet sand with such and such settings and these filters and so on, is it just enough that after these observations all the metadata about it can be created and so, or am I expected to like provide something like information about the run, what was the scientific goal, and so on and so on?
So the question is, what is the role of the observer in providing metadata? And the short answer is you have to provide a lot of metadata into when you put your proposal together. And certain of those fields will be propagated into the files. Okay? And that's your only responsibility. You don't have any responsibility beyond that to provide more information. Yes, ma'am?
With regards to how the huge amount of data is going to be downloaded from the telescope to the data center,
Mm-hmm.
is it going to be, I wonder, in a form where automatically some bad data are deleted and only the good ones are downloaded to the data center? How is this going to work?
So all data that comes to the data center will be kept, unless there are some huge resource problems going forward. There is mechanisms by which technically data could be deleted, but the way we find out about, because we download the data from the telescope, our responsibility is to make sure that exactly what was on the telescope ends up at the data center, bit by bit. When it comes to processing the data is when we work out that something went wrong. But we will not actually, even if we discover that the data is complete crap, we will not delete that data. We are charged with keeping that data. So unless at some point in the future, there is some great resource problem and we really need to free up a whole bunch of space and there is a lot of really crap data, which there will not be, then we will keep that data forever, at least at the raw level. It will never end up as processed data, probably.
So you will have backup resources for days when SIM is so good that you have 66 terabytes of data. Backup resources to download everything.
Yeah, yes.
Okay.
And sorry for not repeating the question, Claire. Yes, question was whether or not we'll have backup resources for downloading 66 terabytes of data. The answer is yes.
Is there a geographic or cloud backup in case this building gets flooded or is that?
Question is, the question is, if the Yellowstone volcano goes up, do we have a backup somewhere other than in this building? And the answer is yes. We will have a tape backup remote to this site.
How remote?
How remote? Remote enough.
For the Yellowstone,
For the Yellowstone volcano, I think it's remote enough.
that's like Mars or something.
Remote enough for the Yellowstone volcano to pick those up properly?
Yeah, I think so. Listen, it's remote enough for the Yellowstone volcano. For our current president, maybe not. Oh, political joke there. So yes, we do have backups, both locally of the data and remotely.